And welcome back, everybody. All right, so the undefined case for Extrema. Um, the previous video was this one, the intro to Extrema. Now we are going to have a discussion on the undefined case. Okay, so we're going to look at this graphically first. Okay, there's a few different situations we need to be aware of. So here we go. All right. Little tiny review, okay? And I'm just gonna come over here. Remember, for a minimum, we need the derivative to be 0 or undefined. And we need the sign, SIGN, of the slope to change from negative to positive. Woo! Woo! Sorry. For a maximum, we need the derivative to change from positive to negative. Okay? So, just to keep it simple, just think about these little pictures, right? For a minimum, we need this. For a maximum, we need this. Okay? Negative to positive slope, positive to negative slope. Okay? Let's remember that. Okay? Now, we're going to focus in this video on this case here, the undefined case. All right? So, first, very typical situation is this one. Very typical. All right? It's typical to have something like this. This is like an absolute value thing. Absolute value functions kind of look like this. There we go. Here's a situation. And now here, we could also have something like this. Yeah, something like that. And then we could have this situation. Asymptote. Yeah, just kind of keep it like that. All right. So like I said, again, here's an asymptote. I want to draw this vertical little dotted line here to just represent the asymptote. Okay. All right. And let's give these... Last time we did numbers, let's do letters this time. Because you could very easily be asked a question in terms of letters. Let's say this is x equal a. Let's say this is x equal b. Let's say the asymptote location here is x equals c. And we'll keep it like that for now. For the y values, we'll just say, I don't know, we'll say this one's 4. And we'll say this one's like, I don't know, -5. All right. Okay. So, let's look right here. Okay, here's situation 1. Okay. So, so f is continuous here. I'll come over here. F is continuous at x equal a. Okay? We do not have to lift our pencil. Okay? However, the slope is not continuous. Okay? So if I look to the left, remember the left has to be... Anyway, sorry. Apologize. Let's look to the left of this point. The slope here is positive. Okay? So the slope to the left in this little case is positive. And the slope to the right, you can see we're decreasing here. The slope to the right is negative. Okay? But not only that, this is a corner. Okay? And let's remember that dy dx does not exist. dne does not exist at corners. And now you might be thinking, well, why is that? And the reason is because the slope jumped. The slope jumped from like positive whatever. It looks like it's about like positive 2 or something. It jumped straight from positive to negative. It did not smoothly, continuously change from positive to negative. It instantly changed from positive to negative. One instant, the slope was positive whatever, and then the very next it was negative whatever. And that's what gives rise to this little corner here. Okay? And let's remember that, you know, the derivative is a limit. Okay? The derivative is a limit. Okay? And so a limit has a left hand and a right hand side. So the way you need to think about this is, does the left hand slope approach the right hand slope? And they do not. This is positive. This is like positive. Let's just say it's positive 2. This is negative 2. Okay. I know that we actually don't have those numbers up there, but it instantly changes from positive something to negative something. So there's not a continuous change here. Now this curve, on the other hand, if we just look at this little logarithmic looking thing here, this slope does change continuously everywhere. If we just look from here to here, okay. So this is what, you know, a continuous deformation of slope looks like, or a continuous change in slope looks like, versus a gap in the slope, a jump in the slope, a corner. Okay, so this is the first case where dy dx is undefined. That's the big point I wanted to make here, is that at x equal a, come down here, at x equal a, dy dx, the derivative, is undefined. Okay, now we're getting to the big point. Okay, now we're getting to the big point. Even though the derivative is undefined, we still went from positive slope to negative slope. Okay, so we still have a max at x equal a. Specifically, we have a local max at x equal a. Okay, so this is what it means when they say, you know, figure out where your slope is undefined, right? So if you have a graph, you're looking for corners and things like that, this is going to show up if you have an absolute value function, right? So if you have like absolute value of 2x minus 1 or something like that, you're going to have a corner at x equal 1/2. Okay, and then that's going to give you actually a minimum. Okay, so anyway, so there's that. And actually, you know what? Let's actually do this. Okay, so we're going to do an example. Oops, I'm going into my last video there. Oh no, I'm running out of space. Imagine that. Let's do. I'm trying to do 2 examples, if possible. One. Let's take an in-depth look at the absolute value of 2x minus 1. Okay. So again, you know, this is an absolute value function, so it's going to have that V shape. Okay. Let's remember that the absolute value of any number is literally that number if that number was positive. In other words, absolute value of 5 is 5, absolute value of 10 is 10, absolute value of 100 is 100. Okay, but the absolute value of x is the negative of x if x is negative. Okay, so in other words, you know, the absolute value of negative 10, if x is negative 10, the negative of negative 10 is positive 10. Okay, so we're going to apply that right up here. Okay, so let's get 2x minus 1. Let's set that equal to 0, and let's solve. If we add 1 divided by 2, we get x equals 1/2. Okay, so what this means is that if x is bigger than 1/2, then the absolute value of 2x minus 1 is exactly 2x minus 1. However, if x is less than 1/2, then the absolute value of 2x minus 1 is the negative of 2x minus 1. Okay? So now, now we can kind of look at this thing. Okay? So we have, let's say this is x equal 1. So 1/2 would be here. Say this is 1/2. Okay? And this is where everything changes. Okay? So to the left of 1/2, it's going to be negative 2x minus 1. In other words, it's going to be like this. Okay. So this point has to be 1. Okay. Now to the right, it's going to be exactly 2x minus 1. Okay. So what I've done is I have just plotted the absolute value of 2x minus 1. That's all I've done here. Okay. Now, let's look at the left portion. Okay. So we're looking here. We're looking at the left portion. Okay. So the left portion. So let's call it y left. YL for y left. This is going to be the negative version. Okay. So negative 2x minus 1. We can do some algebra here. Negative 2x plus 1. Okay. Now, let's calculate the derivative. This is going to be negative 2. Okay. Now, on the other hand, let's look at the right-hand side. The right-hand side is 2x minus 1. If we take its derivative, that's just going to be positive 2. Okay? And now, once again, let's remember the derivative. The derivative is nothing more than this limit. Limit as h approaches 0. F at x plus h minus f at x over h. And let's remember this limit has a left-hand limit. In other words, like a left-hand slope, okay? And this has a right-hand limit, okay? These have to be the same if this is to exist, okay? But as we can see, the left-hand derivative is negative 2. The right-hand derivative is 2. These are not the same. Okay? So this is the reason. This is the reason why the derivative at 1/2 does not exist. Okay, because the left-hand derivative is not the same as the right-hand derivative. This is going to be the case for any corner in the world. Okay, your derivative is undefined, but even so, look at what happens. Okay, at x equal 1/2. Okay, the left-hand slope, I'm going to abbreviate here. Left-hand slope is negative 2. The right-hand slope is positive 2. So we went from negative to positive, okay? So it's kind of like this, except instead of being smooth and continuous, it's like this, negative to positive. I still have a minimum down here, okay? So even though my derivative doesn't exist, I can still conclude safely, because of this, that we have a minimum, because we went from negative to positive. We have a minimum at x equal 1/2, and of course the y value will be 0 for that. Okay? Very nice. Okay. So how long was that? 14 minutes. Let's go through one more thing. Okay, and at this point I do need a new layer. Surprise, surprise. All right, let's turn that bad boy off. All right. So now, oops. Okay. So now, let's go through this little example here as soon as I find it. I had it. And now I can't find let's try this. Let's see how this goes. Here we go. This should be interesting. X over x cubed minus 1. Okay. And again, you know, what we're looking for here is we're looking for max and mins. Okay. So, all right, cool. So the domain is helpful. If they don't give you one, it's good to find it. Okay, so here we have something in the denominator, and we know we cannot have a 0 denominator. Okay, so we're going to take x cubed minus 1 and set that not equal to 0. We may remember, hopefully we remember, how to factor two cubes. We find the cubed root of each term, and then square this one, plus multiply the two together, and then square the last one. Okay, and we may remember, I hope we remember, but if not, please go through this yourself and make sure you understand it's the case. This is going to produce complex roots every single time. As soon as you factor a difference in cubes, the quadratic that comes from that is always going to have complex roots. And so in calculus, we don't even have to worry about it because there's no real solution. Okay. So we don't have to worry about this. So we just have x minus 1 equals 0, or cannot equal 0. I'm sorry. Therefore, x cannot equal 1. Okay. So our domain then is going to be negative infinity to 1 union with 1 to infinity. All right. Very cool. All right. So now we have that to work with. So now let's remember, for Extrema, we need the first derivative to be 0, or we want the first derivative to be undefined. Okay? In order to do any of this, we need to take the derivative in general. So let me come down here. Let me write the function down again. X over x cubed minus 1. And now this is a quotient, so we're going to have to use the quotient rule for this bad boy. So quotient rule, right? It's going to be bottom, derivative of the top, minus top, derivative of the bottom, over the bottom squared. So let's just go ahead and do that. Bottom, x cubed minus 1, derivative of the top, derivative of x is 1, minus the top, and then the derivative of the bottom, derivative of x cubed minus 1, that's just going to be 3x squared. There we go. And then all this over x cubed minus 1 whole thing squared. Okay. This, I have to say, is interesting. Let's see how this works out. We're going to do some algebra now. X cubed minus 1 minus 3x cubed over x cubed minus 1 whole thing squared. And what's this going to be? This is going to be negative 2x cubed minus 1 over x cubed minus 1 whole thing squared. There's our derivative. Okay? And it appears, just by looking, it appears that we're going to have a solution in the top and in the bottom. So let's set this equal to 0 first, which obviously means the top has to be 0, right? Negative 2x cubed minus 1 equals 0. We're going to add 1, divide by negative 2. X cubed equals 1 over... I'm sorry, negative 1 over 2. Yeah, negative 1 over 2. And so then x is going to be the cubed root of negative 1 over 2. Which is, can be simplified a little bit, negative 1 over the cubed root of 2. So there's critical number 1. And then we also need f prime equals undefined, okay? And that is going to be found by setting the bottom equal to 0, okay? So I'm going to have x cubed minus 1 squared equals 0. All right, number squared equals 0. That means the number itself has to be 0. So square root both sides, in other words. If I square root both sides, I get x cubed minus 1 equals 0. This is going to give me x cubed equals 1. And it's going to be x equals 1 and 1 only. All right. So we have two critical numbers. Let's go ahead and list them. Critical numbers. We have x1 is negative 1 over the cube root of 2. We have x2 is 1. All right. Okay, so now we're going to take our domain and we're going to split it in terms of our solutions. Here's our domain, and 1's already in there. The only thing we have to include is negative 1 over the cube root of 2, which is obviously going to be to the left of positive 1. So intervals, yeah? Let's set up our intervals. So this is going to be negative infinity to negative 1 over the cube root of 2. Negative 1 over the cube root of 2 to 1. Oh, wow, out of space. Woo! I'm never ready for it. So I guess I'm going to come up here. Sorry, 1 to infinity. Okay. Cube root of 2. Cube root of 2 is like bigger than 1. 1 over number bigger than 1 is, this is going to be like negative, it's going to be less than negative 1. I want to be safe, and I want to choose negative 2 to test. Here I go from negative to positive, so I want to be easy and choose 0, and here I'm just going to choose 2. All right. So now, where is our derivative? Our derivative is right here. Okay. So we got to plug into this guy. I'm going to write him down here again. Negative 2x cubed minus 1 over x cubed minus 1 squared. Okay, and before I just start plugging numbers in, because the denominator is squared, it's always going to be positive. So the only thing we actually have to worry about when we're plugging in numbers is what the sign of the top is. So we can save time this way. Again, because the bottom is squared, it's always going to be positive, so we don't have to worry about that. All right, anyway. If I plug in negative 2 to the top here, negative 2 cubed is going to be negative 8. Negative 8 times negative 2 is going to be positive 16. 16 minus 1, still positive. So my derivative is positive, therefore my function is increasing. If I plug in 0, I'm going to have just negative 1. So in other words, I just have a negative here. F is decreasing. And lastly, if I plug in 2, negative. Yeah. 2 cubed is 8. 8 times negative 2 is negative 16. Negative 16 minus 1 is going to be negative 17. So this is going to be negative. F is decreasing. Okay. All right. So let's look at what happened now. Let's put this all together now. All right. So from here to here, we went from increasing to decreasing. Okay. So that means that something like this happened. Okay. And if we remember what that means that we have a maximum. Okay. So again, we have a max at x equal -1 over the cube root of 2. Okay, that's our maximum location. And now let's look here. Here we went from decreasing to decreasing. So there was no change. There was no change. Okay, so what that tells us is that we have no extrema at x equal 1. Okay, no extrema at x equal 1. And by the way, we have a name for that. We call that a saddle point. It's more evident in 3 dimensions why we call it a saddle point. But for now, let's just remember it's called a saddle point. If there was no change. Basically, what happened is this. If you're having trouble visualizing what happened, basically something like this happened. Something kind of like this. Let me think. Yeah, something like this happened. So, if you think about what's happening here, the function's decreasing to the left, and then also to the right, right? If we go to the right, we're still decreasing. So something like this happened. There, here's where the thing was undefined, and then to the left we're decreasing, to the right we're decreasing. So that's what happened. Something like that happened at x equal +1. Okay. All right. And now if we want the y value of the maximum here, we just plug it back into the original function. So again, x is -1 over the cube root of 2. So if we want the y value, we're just going to do f of -1 over the cube root of 2. And that's just going to be -1 over the cube root of 2 divided by, and now if I cube a cubed root, I just get what's inside. This is going to be -1 over 2 minus 1, which is the same thing as -2 over 2. -1 over the cubed root of 2 divided by, -3 over 2. All right, and now complex fraction, not a big deal. We've done a million of these, right? Flip this bad boy. There we go. Negative times negative is going to be positive. We're going to have +2 over 3 cube root of 2. All right, that's going to be the y value of the maximum there. All right, and now really quick, let's see. Let's look at let's look at Desmos. God. Okay, Desmos. And let's just this is this one's a little complicated, but we're just gonna take a look at it. X over x cubed minus 1. x over yeah, see, this is what I was talking about, right? See, as x approaches, because here's 2, so 1 is here, right? So we're going down, 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 decreasing, decreasing, decreasing. There's an asymptote, and then we're still decreasing on the right hand side of the asymptote. So we have no extrema there. And here is our maximum. Okay. So this is that critical number that we found. And let's just make sure that that's what we have determined here. Let me go down. Yeah, maximum. There we go. Yeah, we are good to go. I hope this explains the undefined case fairly well. Yeah. All right. Good.